Hello, everyone, back again for our lecture on ocean water and ocean life. So here we go. It's very important, obviously, that we understand not only the water, but the things living in the water, right? Up until now, we've been able to pretty much ignore biology. Certainly in astronomy, we could ignore biology mostly. We did in geology, although if we had gone much further, we would have needed to start talking about some biological things. But oceanography, there's just no getting around it. I mean, there's stuff living in that water, and it's very important stuff. So we need to talk a little bit about that. But first, we need to talk a little bit about just seawater. So I don't think I'm giving a whole lot away. If I can get my slide to advance, come on, there we go. I don't think I'm giving a whole lot away when I tell you that salt water consists of salt and water, and in particular there's about 35 grams of salt in a liter of water, which would weigh 1,000 grams, so about 965 grams of pure water, and then about 35 grams of salt. Now when an oceanographer says salt, they don't mean NaCl salt. They mean everything that's in that water, right? And so, yeah, certainly, if we look here, let me just make sure you can see me pointing. If we look here, you can definitely see there's sodium and there's chlorine, but there's also sulfate, magnesium, calcium, potassium, and we could go on and on and on. In fact, if you look at a periodic table, every element that occurs naturally is there in some quantity or another in seawater. And and it's seawater, it turns out, is a very complicated chemical solution. And in fact, if you want to be an oceanographer when you grow up, you'll take a whole class in nothing but chemical oceanography, which is just the chemistry of seawater. But there's an interesting question here about where do those salts come from, right? Because if you go swimming in a spring or a lake in Florida, it's fresh water, mostly fresh water. But if you go swimming in the Gulf of Mexico, that's salt water. It's different. So why is the Gulf of Mexico salty, whereas I don't know what Colorado Springs is not, right? Why is that? Well, so where do those salts come from? Well, a couple of different places. Mostly they come from weathering rock on land, right? So the fun thing about water is water will dissolve anything. If something dissolves in a base, it will dissolve in water. If something will dissolve in an acid, it'll dissolve in water. It's chemically just kind of like that. And if I had a dry erase board behind me, I would stand up and show you why, but just trust me, water will dissolve anything. And so as water runs over rocks on land, it dissolves chemicals and gradually carries those chemicals into the oceans where they accumulate. So it's not that rivers in particular are totally fresh water. They're actually not. They got a little bit of salt in them. Not much, but a little bit. And they're constantly putting that salt into the world's oceans. The other thing is underwater volcanoes, right? Underwater volcanoes, like the entire mid-ocean ridge system, right? I mean, when I say underwater volcanoes, maybe here, don't think about, an isolated underwater volcano on the bottom of the Pacific Ocean or something. Think about that entire mid-ocean ridge system as one long underwater volcano, right? And as it erupts, it's going to put all kinds of chemicals into the water. And so so we're adding chemicals. Now let me fast forward real quick here. We're putting about 2.5 billion tons per year of chemical into the world's oceans. But here's the thing, right? Let me go back this time. 35 parts per thousand, right? 35 grams of salt per kilogram of seawater. So 35 parts per thousand. And it's not changing. And yet we're adding, 2.5 billion tons per year. So if we're going to add 2.5 billion tons per year, and it's not going to change, and the salinity isn't changing, which it's not on a short time scale anyway, then we got to remove 2.5 billion tons too, right? That's got to be in balance. So how then do we get that salt out of the water and and maintain around around 35 parts per thousand? Well, a couple of different ways. One of them is chemical precipitation, right? We talked about chemical sedimentary rock. We talked about hydrogenous sediment, which, both, are chemicals one way or another precipitating out of that water. And so that's going to be, if that calcium, carbon, and oxygen are in that limestone, they're not in the water. Right, and so that's one way. The other way is all those little organisms out there making skeletons. Right, you've got all these are foraminifera over here. There's some radiolarians. There's some diatoms. Right, you got all these things living in that water, making a skeleton. And once again, if those chemicals are in that skeleton, they're not in the water. Right, and so those two things kind of balance out. All right, so that chemical, physical weathering of rock on land, underwater volcanoes both put about 2.5 billion tons per year, and then chemical precipitation, organisms making skeletons, they remove salts, and it all kind of evens out at about 35 parts per thousand. Now, seawater is actually very complicated stuff. If you want to be an oceanographer, you're going to learn about chemical oceanography, which is the chemistry of seawater, and then physical oceanography, which is the physics of seawater, and it just goes on and on and on. But really, there are three things that if you can understand them, you'll get most of it, and that's salinity, temperature, and density. Now, we already kind of talked about salinity in terms of the broader picture with the world's oceans, and where does it come from, how does it get out, what is it, about 35 parts per thousand, etc. But that's a very, very big picture, right? If you go out to Tampa Bay, for example, salinity, not so much 35 parts per thousand, right? If you go up to the Gulf of Alaska, it's not going to be 35 parts per thousand. If you go to the Mediterranean, it's going to be higher than 35. If you go, the Gulf of Alaska, by the way, would probably be lower than 35 parts per thousand. If you go to the northern Gulf of Mexico, it's probably going to be a little bit lower, et cetera, et cetera. So geographically, while yes, on average, it's 35 parts per thousand. Moving around, it's not always 35 parts per thousand. That's an average. So what controls that salinity locally then, right? What's the deal with why would the Mediterranean be higher? Why would the northern Gulf of Alaska be lower, etc.? Well, here's the thing to get, right? Once again, not giving a whole lot away here, salt water consists of salt and water. Okay, here's the trick. There's really no way to add or remove a whole bunch of salt in the world's oceans, right? The salt you have is kind of the salt you have. You've got it, washing into the oceans from various places, rivers and whatnot, adding it accumulates, and that's kind of the salt you have. So what we're going to do then is locally, we're going to alter salinity by changing the amount of fresh water, right? And so if we can change the amount of fresh water, that will alter the salinity, right? And so if we add fresh water, that decreases the salinity, right? If we remove fresh water, that increases the salinity of the water. So the way in the natural world you make seawater more or less salty is by adding or removing fresh water. So how do we add fresh water? Well, we already talked about river runoff, oddly enough, as being the source of those salts. But remember, there's not that much salt in there. It's accumulating in the oceans, but there's not that much salt in there. And so rivers are mostly fresh water. And so areas where you have a lot of river runoff, you're going to have more freshwater input, and you're going to have less salty water, right? And so, if you look here, this is I believe the Anclote River here, a picture I just took when I was out there sometime. But this is the Amazon draining the, Amazon rainforest, right? It's dumping a ridiculous amount of fresh water into the world's oceans, and so the water here is pretty dang fresh. In fact, you can be sailing completely out of sight. In the off the coast of this Amazon Delta and be out of sight of land off the coast of the Amazon Delta and be in completely fresh water. It's dumping an awful lot of fresh water into the Atlantic Ocean, and so the salinity goes down there a lot. Another source of fresh water is glaciers, right? Glaciers are these great flowing rivers of ice. Let me go ahead. I had not planned on going to Google Earth, but I think I'm gonna here. Give me just 1 second here, and I'll get Google Earth going here, and we will have that. And there we go. And so let me show you some glaciers, right? And so, if we load it, it's going to take a minute to load because I got a lot of stuff on Google Earth. And load. So how we doing? You doing all right? Dealing with quarantine okay? Yep. Stay home. Wash your hands. Don't touch your face. All that stuff. There we go. Okay, so easiest place to see glaciers. I've shown you this already, but with respect to what we're talking about now, up here in Alaska, right? We can see these great rivers of ice, if you will, flowing down out of the mountains. Now, normally there would be a seasonal pulse here, where in the summertime, the glaciers would melt back a little bit, and you would get a pulse of fresh water, and then in the wintertime they would grow, and you would not get that pulse of fresh water. But we still kind of have that. But then, of course, laid over on top of all of that is just the general retreat of glacial ice as our world is getting warmer and causing there to be, a considerable input of fresh water. You can see here, if I zoom out a little bit, you can see that just here, there's a good one. Here's a whole bunch of glacial valley with no glacier in it, right? We are losing glaciers at a prodigious rate, and as we do that, we're dumping an awful lot of fresh water into the world's oceans, and we'll talk more about that when we talk about global climate change. So yeah, so glaciers, right? Glaciers melting. Hold on, I'll get it all so y'all can see it. Just give me 1 second here. There we go. And so yeah, so as we lose glaciers, we end up dumping a whole bunch of fresh water, right? I was up in Canada couple summers ago, glacier selfie, and here we go with a glacier, but not me. Let me turn my phone off so that I'm not being bothered by people trying to get me with stuff. Hold on 1 second, guys. And there. Okay, so glaciers, right? This is the Athabasca Glacier in the Columbia ice fields, and as you hike up to it, they've got signs along the trail saying, in 1980 the glacier was here, and you can't even see the glacier. And then, in 1985 it was here, and it was here, and it was here, and so we are most definitely warming the planet and losing glaciers. And for our discussion right now, that makes seawater less salty, especially around these glaciers. Another thing, separate from glaciers, but another kind of ice, is sea ice, right? Sea ice is fresh water. Sea ice is what happens when you freeze seawater, but when you do that, and we'll talk a wee bit more about this here in a minute, but when you do that, you make freshwater ice. There is basically no room in ice's crystal matrix for anything other than ice. And so when you freeze that seawater, what you end up with is freshwater ice on top of that seawater. And so if you melt that sea ice, that makes that water less salty, right? And so once again, normally there would be a seasonal pattern to that, and there still is to some degree, but overprinting all of that now is just the general decline in sea ice, right? I have a graph here of sea ice extent, the different colors. are different months. And so, winter months are up here, summer months are down here. But you can see that they're all getting less. We're getting, less ice all the time. I'm going to scratch my eye. We're getting less ice all the time. And, for our purposes right now, that decreases the salinity of seawater. And then, of course, rain, right? Rain is particularly pure water, actually, unless it's got weirdness in it. But mostly it's water, it's pure water. It certainly doesn't have any salts in it, and so yeah, so in areas where it rains a lot, you're going to get fresher water, especially right there at the top. That top few feet are going to get really really fresh in that area. So that's how we add water, right? We can do it with river runoff. We can melt some glaciers. We can melt some sea ice, or it can rain. All right, so those things will add fresh water. So how do we remove fresh water? Right, that seems weird, um, because how do you basically take the water out of the water? Right, I'm not really clear on how not how do you do that? Right, well, two ways. First way, we kind of already touched on, make sea ice, right? If I freeze salt water, what I will end up with is freshwater ice with saltier water left behind. I kind of avoided saying that before, right? Because if I make freshwater ice, that means that the water that's left behind has more salts in it, right? So you can make water saltier by freezing it. In fact, if you were to go out just into the Gulf of Mexico and put some of that water in an ice tray, what you would end up with is like a cube of ice, and right in the middle of that cube would be, I'm trying to get my hands to do this. Right in the middle of that cube would be a little bubble of hyper saline water that is basically too salty to freeze in whatever temperature your freezer is getting down to. So the water that remains after you make sea ice is saltier, right? So you get a seasonal pattern there, where in the wintertime you tend to make sea ice and it tends to get saltier, and then in the summertime you melt it and it tends to get less salty. Nowadays, all overprinted by the larger pattern of global climate change, melting ice. And then the other way, kind of the opposite of rain, is evaporation, right? If I evaporate seawater, what I do is I remove the water, and what's left behind are whatever chemicals or salts are in that water. And maybe you've done this accidentally. I don't know. I've never done it. Yes, I have. You go to boil a pot for macaroni and cheese or spaghetti or whatever, right? And you forget about it, right? And you're off doing something else, and suddenly, oh shoot, I had that. But yeah, and so you go back in your kitchen, and you've boiled the pot dry, and there's this white gunky stuff, this white flaky stuff on the bottom, right? That's just chemicals that were in the water. This just is, and so your water's not totally fresh, and so unless you're cooking with distilled water or something. And so, yeah, well, we'll see. If you were to do that with water from the Gulf of Mexico, there'd be even more stuff left behind, right? When you evaporate water, and boiling is basically evaporating water, you're going to remove the water and you're going to leave behind the salts, right? So if we want to change salinity locally, um, um, what we want to do, remember, is add or remove fresh water, right? So we can add water with river runoff, glaciers melting, sea ice melting, or rain, and we can remove water, hence increasing salinity with either evaporating the water or making sea ice. Either of those will do it. And so locally, that's what happens, right? That's why, the Mediterranean, where it's really, really warm, that water tends to be more salty because you get a lot of evaporation. Down in the tropics, it's warm, but it rains. And so, it varies a lot there, right? If you go a little while without rain, then the salinity will go up. If it rains, the salinity goes down, et cetera, et cetera. And so what's going on at any given time can have a huge effect on the salinity of seawater. What about temperature? Well, temperature in the ocean, at least of the surface water, and temperature on land are both kind of controlled by the same thing, mostly. There's more, but the first thing everyone always thinks about is, of course, sunlight. And when we think about sunlight, what we really want to think about is latitude, right? Because as you go further south, you get more direct sunlight, and that generates more heat. As you go further north, you get less sunlight, and that generates less heat. The fact that the sun is lower in the sky at noon, the further north you go, is why it gets colder as you go up there. It's not that you're further from the sun or something weird like that. And when we talk about the seasons, I got a fancy little graphic for that to kind of explain that to you. But you know, just without necessarily even knowing why, right? Just intuitively, we know that the further north you go, the cooler it gets. The further south you go, the warmer it gets in the northern hemisphere, right? And so maybe we should more properly say the closer to the equator you get, the warmer it gets. The further from the equator you get, the cooler it gets. And that's what's controlling the temperature on land overall, but there's other things too. But on the water, that's what controls the temperature of the surface water. Okay, and so what that means then is that at lower latitudes, so lower latitudes being closer to the equator, okay, you get a lot of heat generated, and that produces, you know, warmer temperatures. So this graph, oceanographers love these kinds of graphs, right? They'll graph something across here, and then they'll graph it as you go down, right? And so hold on, guys. I'm going to pause this and get my water because I talked a lot yesterday, too. Hold on. Turns out it was right behind my computer. Okay, so oceanographers love to graph stuff like this. What they'll do is they will graph, and let me make sure y'all can see me pointing. I don't even know anymore. There we go. So you can, they'll graph something across here. In this case, it's temperature, and they'll graph it as you go down through the water. All right, and so geologists do this too. But anyway, so you can see here that, you know, the temperature of the surface water at lower latitudes near the equator is very warm because it's been heated by the sun. As you go down, though, that temperature drops off. That change in temperature as you go down is called a thermocline, and oceanographers, oh my gosh, they love their something oclines, right? Something cline is just a change in something as we go down, right? And so a thermocline is a change in temperature, a halocline is a change in salinity, a pycnocline is a change in density. I mean, they'll put anything in front of ocline and talk about how it changes as you go down through the water. And so here you can see that, you know, around 500 meters, that's going to be about 1,500 feet down, you know, the bottom just drops out of the temperature because there's no more sunlight, right? The only real source of heat consistently in the ocean is sunlight. So once you run out of it, you're done, right? And so the lower latitudes near the equator, you know, the sun is powerful enough to heat that surface water, but it's not going to heat the deep water. It's just not. Now, at higher latitudes, further away from the equator, curve looks like that. That blue line I just drew, right? It just goes up. The surface water is cold. The deep water is cold. The very deep water is cold. It's all just cold. It's all just you know, barely above freezing, right? And so this thermocline is something that happens in, you know, tropical to subtropical oceans where you have that warm surface water. So, you know, so we can talk about, you know, a few different kind of layers based on temperature, right? Where you have a surface zone heated by the sun, 300 to 450 or so meters deep. You would have a transition zone that contains that thermocline, and then a deep zone, right? And so, you know, this is what that looks like, right? I've got a surface zone up here, not a whole lot of the water. It's only about 2% of the water. That's the warm, good water that organisms are really going to want to live in. Transition zone where the temperature is falling, and then deep, cold water down here, which is most of the world's oceans are in here. Now, this is a very stable thing, right? Because, this colder water is more dense. It wants to sink. It's already on the bottom. The warmer water is less dense. It wants to rise. It's already on the top. So you get this kind of layering, and it's a very, very stable thing. This water is not going to want to turn over a whole lot at all. In fact, it's going to be a little difficult to get it to do that, but we'll talk about that next time. So just now when I said, okay, look, the colder water is more dense and it wants to sink, and the warmer water is less dense and it wants to rise, and everything is stable, that brings us to density. Okay. So remember, we've been in and out of density for the entire class, right? When we were talking about Jovian versus terrestrial planets, we talked about density. Let me move my computer so I'm more in the thing there. Is that better? Nope, I just moved it the wrong way. There we go. When we talked about Jovian versus terrestrial planets, we talked about the density difference between them, right? When we talked about rock, we talked about the density of minerals and the density of, oceanic crust versus continental crust and all that kind of stuff. Was important in water too. Now, there's two things overall that affect density. Remember that density, let me just make sure we're all on the same page here, that density, remember, is mass per unit of volume, right? It's how much does something weigh compared to how much of it you have, right? It is the difference between, a brick of brick and a brick of styrofoam, right? Same size, different mass, because they're just made of different things, right? And so, yeah, so water has density too. And there's two things that affect density of water. Temperature and salinity, right? Because see, here's the trick, right? Usually, when we measure density, we're measuring it relative to water, right? Something that has a density of 1 weighs the same as an equal volume of water. But if I was being really correct and proper about this, I would need to say fresh water at room temperature. I don't know what room temperature is. I'm sure someone has a temperature for that, right? You have to specify those things because those things affect the water's density, right? If you change the temperature of water, seawater or fresh water or any water, you change the density, right? Cold water is more dense than warm water is, okay? The other thing you can change though is the salinity, right? If you add salt to the water, salt water is more dense, fresh water is less dense. Let's go back to that temperature thing because there's one weird thing that water does, right? The density of water, if you cool it, the density of water goes up and up and up right until it freezes and turns into ice, and then it drops right down, right? Ice floats, right? Ice is actually less dense than liquid water, or it wouldn't float, right? Nothing else does that, guys, right? There is nothing else where the solid version of it will float in the liquid version of it. And, I know we're not used to anything else like doing anything like that, but I'm just telling you that, if you have solid mercury, it will not float in liquid mercury. It'll fall right down to the bottom. If I have a piece of solid iron, it will not float in liquid iron. It'll fall right down to the bottom. And yet, solid water floats in liquid water. It's very, very strange, but it does. And so, but for our purposes, doesn't matter. Okay, as long as the water remains liquid. Okay, if you cool it, it will get more dense. If you heat it, it gets less dense. Okay, salinity. If you add salt to it, it gets more dense, or if it's more salty, if you do it by removing the water. Saltier water is more dense, fresher water is less dense, right? Now, so here's the oceanographer's version of density with depth. Notice the scale, right? We're not talking about huge differences in density, right? We're talking about the difference between 1.023 and 1.029, right? It's not huge, but it's there. And you can see that as you go down, the density tends to go up. Well, we already saw this, right? Where as you go down, the temperature goes down, and you can see that right there, as the temperature goes down, the density goes up, right? And so the reason I'm showing you this is to make the point that, yeah, while both salinity and temperature can affect the density of seawater, temperature is more important, usually. Okay, there are weird extreme cases like the Dead Sea where it's just so salty that anything will float. Okay, but under normal circumstances, okay, um, temperature is more important than salinity. You have to change the salinity a lot to get the density to even change a little bit. On the other hand, temperature, you jack the temperature around by just a few degrees, and you can radically alter the density. So they're both possible, and there are cases where salinity is more important, but day in day out, temperature is more important. Okay, so now that we know a little bit about the water, let's think about the things living in the water. And so, if this were maybe a marine biology class, we might talk about this, but we would also talk about that, like the Linnaean classification scheme, where you have, kingdom, phylum, class, order, family, genus, species, and stuff like that, and we would classify things that way, and that's fine. But there's an easier way to do it, and a way that is a bit. I'm obsessing about how centered I am in the picture for some reason. I don't know why. Anyway, there is an easier way to do it. And that is an ecological classification. Now, ecology, is one of those words that has been kind of co-opted by the nouveau hippies to mean I don't even know what they think ecology means. But for our purpose as scientists, ecology is the branch of biology that deals with relationships between organisms and relationships between organisms and their environment, right? How are you feeding? Where are you living? How are you living? What time of day are you living, right? How are you finding mates? How are you reproducing, right? All these things are ecology, and it's a very, very complicated division of biology because there's a lot of stuff that we don't know, about how these ecosystems work, about how organisms actually do, relate to each other. And so we're going to have a pretty simple way of thinking about this, though. And we're just going to ask ourselves, how do things kind of generally live and feed and exist within the environment, right? And so the first category is plankton. So plankton, and I couldn't resist, plankton from SpongeBob. I don't even know if people watch SpongeBob anymore, but anyway, there's plankton from SpongeBob. Plankton. Plankton. Now, when I say plankton, you probably think small, and that's generally good, but it doesn't actually mean that. What it actually means is things that float as opposed to swim in the ocean, right? So they can't really swim. They just kind of move around. They just kind of float around, and that's what they do, right? There's two kinds, phytoplankton and zooplankton. Whenever you see that prefix phyto, think sun or something like that, right? Phytoplankton can use sunlight to carry out photosynthesis. So that is the base of the marine food chain, right? We're used, here on land, the main photosynthetic organisms are plants. There are no plants in the ocean. Okay, and that thing that you're thinking about right now that you think is a plant isn't, unless you happen to be thinking about mangroves, which don't really live in the ocean. Okay, that thing that you're thinking about, kelp or seaweed or something like that, it's not a plant. It's algae. Okay, it might be overgrown algae, but it's algae. Salt water kills plants, right? I mean, it just does. And so there are no vascular plants living in the ocean. And so where is, the base of the food chain coming from? Where is that primary productivity, right? That first step, those first organisms that can take sunlight and nutrients and turn them into living tissue. Where is that in the ocean? It's the phytoplankton. Right? It's those phytoplankton. That's the base of the marine food chain. Without the phytoplankton, nothing else is going to work. You have to have those phytoplankton, and they have to live, right there near the top of the water because they need that sunlight. And so phytoplankton, very important. And then kind of the next step up in the marine food chain is zooplankton, right? Zooplankton are plankton, but they eat the phytoplankton. They can't do photosynthesis. They need to eat. They are animal like, right? Hence the zoo. You might be wondering why I have a picture of a giant jellyfish down there in the lower right. That's because it's plankton. right? Remember, it doesn't need to be small, it just needs to float. And if you've ever seen a jellyfish, you know, under normal circumstances, they're not the best swimmers in the world. They kind of, they kind of go, bloop, and then they kind of end up kind of like right back where they started. And so, yeah. And by the time you're a jellyfish, it's, I don't know, 30 feet long. You're not swimming anymore. You really are just floating. Technically plankton, but really when we say plankton, we really are usually talking about the small stuff. Phytoplankton, if it can do photosynthesis, zooplankton eats phytoplankton. If you can swim, you're nekton, right? And so, this is going to be, dolphins, porpoises, whales, fish, stingrays, I don't know, anything that can swim. Okay, it's called nekton. Nekton are most abundant near the continents, right? And this is the thing I want you to get. And we'll talk more about this here in a few minutes. Do not assume that all of this biology that you see going on around you in the areas around Pinellas County and the areas near shore, all around you is the way it is everywhere. It's not. Those areas near shore are the most biologically active areas in the entire ocean. If you're out in the middle of the ocean and you're fishing to live, you're gonna starve. You're not gonna. There's not that much out there. It's all up near the continents, and we'll talk about why. But it is. So yeah. But anything can swim is nekton. So if it's floating in the water and not swimming, it's plankton. My face. It's floating in the water and it's not swimming, it's plankton. If it's swimming in the water, it's nekton. Right now, if we go to a coral reef, let's go to John Pennekamp State Park down in the Keys, and let's jump off of a boat. And what do we see? We see this amazing coral reef. And we can start dividing up those organisms too, because those things, most of them are benthos. Most of them are living either in or on the bottom. Now there's going to be fish swimming around; those are the nekton, right? There's plankton in the water too, right? But when we think about the organisms that make up, say, a coral reef or something like that, they're benthos. These are things that are living either in or on the bottom. Okay, two broad divisions: epifauna and infauna, right? Epifauna live on the sediment. That Greek prefix epi means on top of, right? Like the epicenter of the earthquake, right? The epicenter isn't the very, very place the earthquake happened underground. No, it's the point on top of where the earthquake happened, right? Epifauna live on, not in the sediment. And then infauna live in the sediment. They live buried. Okay, we'll come back to them. Let's go back up to epifauna for a minute, though. If we think about epifauna, so we're thinking there about corals, sponges, sea fans, but then also things like crab, shrimp, lobster, sea urchins, starfish, things like that, right? So that's two different categories of animals, right? Some of them are attached and some of them can move around. If they're attached, like a coral, right, they're called sessile. Like corals are animals, guys, right? There's a weird thing about the marine realm. You look at something, oh, that's a plant. No, it's not. It's an animal. Oh, well, that's an animal too. Nope, that's an animal, right? It's very, very weird. We're used to animals that on land that have legs and heads and eyes and arms and things, and and they don't always have that in the ocean. They really don't, right? The corals are animals, vaguely related to jellyfish, actually. And so, but they're living attached. They make a shell, they attach themselves. That's how they live. They live attached. Okay. So same thing with sponges, right? They live attached. Sea fans, they live attached. There's a whole bunch of animals out there in the ocean that live attached to the bottom. When they live attached, we call that sessile. If, on the other hand, they can move around, we call that vagrant, right? Vagrant doesn't necessarily mean a bum. Vagrant just means that you move around a lot, okay? And so, so organisms that move around, we call them vagrant. When I think of vagrant epifauna, the first thing that I think of is anything that tastes good with lemon and butter, right? So crab, shrimp, lobster, right? They all live on the bottom, and they move around. Okay, vagrant, but also things that we don't, well, most of us don't eat. Starfish, right? Vagrant epifauna. They didn't look like they're moving. They are moving. They're just moving very slow. Sea urchins, also vagrant epifauna, also moving very slowly. In fact, by the way, if you have an aquarium with a starfish and a sea urchin in it, I have bad news for your sea urchin. That starfish is trying to catch it. Starfish are voracious, slow motion predators. They really are, and so I guarantee you, your starfish is chasing your sea urchin around your aquarium. Um, and eventually we'll probably catch it. So yeah. So anyway, so that's epifauna. Infauna are just living buried. That's pretty self-explanatory. But there's a lot of things that live buried. Right? There's a lot of clams that live buried. There's a lot of worms. Oh, there's a lot of worms living buried. A lot of more worms than you want to know about living buried. Right. Next time, when the beach is open back up again and you can go to the beach again. Next time you go to the beach, dig a hole near the water. See what you get. You're gonna get all kinds of stuff. There's all kinds of stuff living down there. And maybe you're like, no, I'm not digging a hole. Okay, but if you want, dig a hole near the water. You'll find stuff. I promise you will. And it's in fauna. It's stuff that's living buried. I thought about getting some more spectacular pictures for this, but I like this one. You can see here plankton living. They're magnified. They're not literally that big usually. Living, floating in the water. Phytoplankton would be doing photosynthesis. Zooplankton would be eating the phytoplankton. Plankton, nectons swimming around, and then benthos, right? Epifauna living on the sediment, infauna living buried, sessile epifauna, attached, living attached, vagrant epifauna able to move around, right? And so there we have a nice kind of ecological classification. And the nice thing about it is, like as a paleontologist, in particular paleoecologist, the organisms that occupy these spaces, and we can use the fancy word for these, niches. The organisms that occupy these niches change through time. Right now, the big, sessile epifauna is coral, right? Coral reefs and coral this and coral that. Well, before coral, something else had to do that, or something else did that, and you'd be surprised at the organisms that were filling that big sessile epifauna niche, through time. And so it gives us a nice way to compare things across time and space as to what organisms are occupying these niches. There's your handy sciencey word for the day. Let's talk about though the things that control where organisms are living. Right, I've got my arm propped up on my cup here. And so where not everything lives everywhere, right? And that. I mean, it's a true on land too, right? I mean, if you start driving northward from South Florida, you're going to run out of alligators inland. Probably around Valdosta, Georgia, or maybe Macon. They're not going to have the alligators anymore. Over on the coast, they go up further. They go all the way up into North Carolina, over on the coast. But inland, by the time you get to New England, there's no alligators, right? Nor are there any palm trees, et cetera, et cetera, right? Not everything lives everywhere. And so we want to take a little bit of time and talk about, in the marine realm, what are the environmental factors that control where an organism does or does not live. The other thing to keep in mind is that while there might be a set of organisms under which, a set of conditions under which an organism might live, you're probably going to have another and stricter set of conditions for them to reproduce, right? And this is, of course, the bane of zookeepers everywhere, right? We all know what it takes to keep a whatever alive. We don't always know what it takes to get them to breed. Not everything, right? Rabbits, not a problem, right? You got a boy rabbit, you got a girl rabbit, you got a rabbit farm, okay? Other things, things like giant pandas and, some birds and things, they're a lot pickier. And a lot of times we just don't know, what it is that triggers that reproductive cycle. So if we just say, well, let's just breed it in captivity, you can't always do that. you cannot always do that. And so a lot of times there's something that triggers that reproductive cycle in nature that's not in that zoo, and we don't always know what it is. And so it can be a little bit tricky sometimes. But let's go back out into nature and ask ourselves, okay, what are the things that really do control where organisms like to live? Okay, well, sunlight, right, is a big one, right? And it's a big one on land too, right? I mean, you buy a plant, and there's going to be a recommendation for well, how much light should this plant get? Should it be in full light or partial shade or full shade or whatever? I don't know. I just kill plants. I don't grow them. But anyway, probably because I ignore the sunlight. But anyway, right. So that's a thing everywhere. What's a thing in the ocean too? Um, we have three zones relating to sunlight, right? The upper part of the water column, where sunlight can penetrate, is called the photic zone, right? And so that's where there is sunlight. That's the photic zone. Now, how deep the photic zone is really depends on a number of things, right? First of all, anything in the water is going to shallow up your photic zone, right? That could be sediment, that could be plankton, or other things, right? Anything in the water shallows up your photic zone. Time of day matters, right? At night, there's no photic zone, right? Okay, and then at noon, by the sun, it's as deep as it's going to get. Time of year also matters. In the summertime, the sun is higher in the sky at noon. That's going to penetrate further and make the photic zone deeper. In the wintertime at noon, the sun is not as high in the sky. That's going to shallow up the photic zone too, right? So that the depth of the photic zone is kind of a moving target throughout the day. And once again, an influx of sediment, a plankton bloom, anything like that will shallow it up. Now, here's the thing, though. Just because you have sunlight doesn't mean you have enough sunlight to do photosynthesis, right? And I'm about to show you a diagram of this, but so at the top of the photic zone, we have the euphotic zone, right? This is where not only do you have sunlight, but you have enough sunlight to do photosynthesis, and it's only about 100 meters deep, only about 300 or so feet deep, right? And so below that, yeah, there's sunlight, but it's this dappled, moody, trying to get my hand in the picture, moody sunlight that, you can't really do anything with in terms of photosynthesis, right? And so the photic zone is where there's light. The euphotic zone is where there is enough light to do photosynthesis, and then underneath that there is the aphotic zone, and that's where it's dark, and that's about 80% of the ocean is this dark, cold water, right? Let me show you on a little thing here, right? And so photic zone, right? That top bit of the water where there's sunlight. Okay, euphotic zone is actually the top of that photic zone, where there is not only is there sunlight, but there is enough sunlight to do photosynthesis, right? And then underneath that, there is the aphotic zone, and this is most of the water out there where there's no sunlight. That water, and if there's no sunlight, there's no heat, right? That water is cold. That water is deep and dark and cold, and not very hospitable place to live, although some things do. This is a fun fish. I like this fish. This is called a coelacanth. Is a very, very primitive fish. You can see that it's got a heterocircle tail. It's got fins that are just busting out to be arms. It's got an armored head. It's a pretty big fish. You can see there's a scuba diver behind it. It's a few feet long, and it is, like I said, a very primitive fish. We thought they went extinct. Now, when I say we thought they went extinct, I don't mean we thought they went extinct in 1982 and no one saw one since. No. We thought they went extinct like 150 million years ago. We have lots of fossil coelacanths, but we don't have, for the longest time, we didn't have any modern ones, right? And then a museum curator named Courtney Latimer, this would have been around the turn of the 1920s, 1930s, found one in a fish market in Madagascar in Africa, um, and she realized what it was. She's like, that's a coelacanth. And she's like, can I buy it? And the guy's like, sure, you want me to cut it up? And she's like, no, 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 no. Just give me the fish, give me the fish. And so she takes the fish. Took her forever to convince anyone in London at the at the Big Banshee Museum that she had what she said she had. She's like, I got a coelacanth, and they're like, oh, you mean you found a fossil? No, no, no. I have a coelacanth that was swimming around the Indian Ocean, 2 months ago. And they're like, yeah, no, you don't. And she's like, no, I really do. And so finally they believed her. And sure enough, she had coelacanth. And so the fish is actually named Latimeria. After Courtney Latimer, but it lives in that deep, deep, dark water usually, which is why we didn't know they were there. There's a lot about what goes on down there that we don't understand, and this was a big one. I mean, we can cut the guys at the museum a little bit of slack because honestly, telling them you have a coelacanth is about like telling them you have a dinosaur in your garage. I mean, who's really going to believe you unless you have a bird, but you know what I mean. So yeah, there's a lot of weird stuff living in that deep water, and I just wanted to tell you about the coelacanth because I just think that's really cool. Okay, so sunlight's important. What else is important? Distance from shore is important because what happens is as you get further from shore, environments get more and more stable. Okay, but there is going to be a sweet spot. And so, our first zone, if you will, when we talk about distance from shore, is of course not of course, is the intertidal zone, right? This is going to be that area between the high tide line and the low tide line. Right now, on the beach in Clearwater, it's about 4 feet, right? It's not that big, right? But but nevertheless, in some places with higher tidal ranges and shallower slopes, you could have a lot of distance there. In fact, I think I've got a picture of this. Hold on one second. Yeah, there we go. That I took that picture off of off the causeway over to Tampa during what's called a spring tide, when tides were particularly low. And here's the tide gauge. I snapped this from my iPad right as I took the picture, and you can see, it was low tide, and there's a few hundred feet worth of tide flat there, worth of mud flat there, and so that is also intertidal zone. If we go to California, the intertidal zone has a lot of tide pools, these little depressions in rock with entire ecosystems existing right there inside of that tide pool in a nice little self-contained ecosystem. They're actually, ecologists are awfully fond of their tide pools for various and sundry reasons. So that intertidal zone right there between high tide and low tide. And then right there near shore, like when you go to the beach and you go in the water, you are in what we call the wave wash tidal zone. That's going to be that relatively shallow water very near the beach. Right here we are in California, in this area right in here, right? This is the area where the wave energy, we'll talk about this more next time, is reaching all the way down to the bottom, right? So if you're going to live in here, you need to be able to deal with that wave energy one way or another. You either need to not care if you get tossed around and ripped up, or you need to be sessile and attach yourself to a rock or something. But one way or another, if you're in that wave wash tidal zone, that shallow water near shore, you're going to get beat up with waves. Now, if you move just a little bit into a bit deeper water, you can still be on the continental shelf but get underneath those waves. That wave energy, we'll learn next time, reaches down to a depth of 1/2 of the wavelength. So if you're deeper than that, you won't even know the wave is there, right? This is where you want to be, right? This is definitely where you want to be. This is called the neritic zone, and this is the garden spot of the world's oceans. The water is shallow, it's warm. You have, it's all in the euphotic zone all the way down. You have a lot of nutrients washing in from land. The bottom, you can live on the bottom and not be in very, very deep, very, very cold water. And it's deep enough that the waves go right over your head and you don't even know it, right? This is where you want to be. Even things that live out here come back up in here to have babies all the time, right? That is absolutely where you want to be, is in the neritic zone. And so once again, all of this biological diversity that you see near shore does not extend out to here. It does not extend out into what we call the oceanic zone, right? This is that deep water offshore. It's not that nothing lives out there. Things certainly do live out there, but many more things live up in here in the neritic zone and the wave wash tidal zone and even in the intertidal zone. And so we sorry, take a breath, Paul. Right, we have this idea that the oceans are this great big huge place, and we can just do pretty much whatever we want, and we can't possibly affect them, and we can. We tend to affect up in here the most, which is where everything, including us, is living. We don't tend to affect it out here very much, where nothing is living. We also tend to affect the top layers of the water where all those phytoplankton are living. We tend to affect it much less out down here, where there's there's stuff living there, but not much. And so we tend to affect, or let's just pollute, right, those very parts of the ocean that we need the most to be healthy. And so there's my little hippie hat for the day, and we'll move on now to water depth. Your book is kind of funny about water depth. And at least it was. I don't know. I haven't checked it lately. And they say, yes, there's water depth. And then they say, look, we're going to classify it, and here we go. And they say anything living in the water at any depth is in what we're going to call the pelagic zone. And that's fine. I mean, that's fine. I just want to show you what actual oceanographers do. This won't be on the test. You don't need to memorize it. But actual oceanographers do say, look, we can divide the pelagic zone up into the epipelagic, mesopelagic, bathypelagic, abyssopelagic, and hadopelagic, right? Getting deeper and deeper and deeper. We won't worry about that. Sure, for our purposes, anything living in the water at any depth will be said to be in the pelagic zone, and that's fine. Anything living on or in the bottom is in the benthic zone, right? And so, we that's a word we heard just a few minutes ago when we talked about the benthic or benthos ecological community. Same word. It's just now we're referring to an environment, and that's the benthic zone. If you're on the bottom or in the bottom, in very, very deep water, then now you are in the abyssal zone, right? And the abyssal zone is that deep water, so high pressure. When you think about water pressure in the ocean, by the way, add half a pound per square inch for every foot you go down. So, or just divide the number of feet down by 2, right? So 10,000 feet of water is 5,000 pounds per square inch. 1,000 feet of water is 500 pounds per square inch, right? And so, by the time you are in, 10, 15, 20,000 feet of water, that's a lot of pressure. And so you have to deal with that. It's going to be dark down there. I'll come back to the food here in a minute, and it'll be cold down there, right? There's no sunlight. So if you're in the benthic zone, you're in or on the bottom. If you're in the abyssal zone, you're in or on the bottom, but in deep water. Okay, now. What about that very little food? Well, that's true. There's not a whole lot to eat down there. Okay, but there are a lot of nutrients down there. And this is going to play right into our next lecture. And so let's talk about where those nutrients come from. Now, nutrients aren't the same thing as food, right? Nutrients are chemicals that biological organisms need, but that doesn't mean they can just eat them, right? You cannot eat fertilizer. Right, nutrients are fertilizer. Okay, you need, in our case, you fertilize the grass. The cow eats the grass, and then you eat the cow. Right, you cannot eat the fertilizer. It needs to be biologically available to you. Okay, but there's a lot of nutrients down there. Where do they come from? Right. Well, let's think about this a little bit. Okay, so, and this is the thing, by the way, that my students, when they see me years later, this is the one thing from the entire class that y'all generally remember. And here it is, right? So here's the surface of the water is the blue line, the bottom is the black line, and so swimming around near the surface of the water, you have fish swimming around doing their fish thing, right? And of course, they're animals, so they eat. And then, of course, after they eat, they need to go to the bathroom, only they don't have a little fish bathroom, and so they just kind of basically go to the bathroom in the water. And yes, this is what people remember. And so, and it's not this one, right? All the fish are, eating and going to the bathroom, and they're basically pooping in the water, right? And so the professor who explained this to me called it the fecal pellet express. He said, look, these fish, they put out this little pellet that is, resistant to falling apart. Some of it gets taken up in the upper water, but a lot of it makes it down into the deep water, right? And in the deep water, there's no photosynthesis, right? There's a lot of nutrients because the fish are fertilizing the water, basically. So there's a lot of nutrients, but there's no sunlight. And so those nutrients are going to go unused. Once again, you can't eat fertilizer, and they accumulate. And so if we can get that nutrient-rich water up to the surface into the euphotic zone, that will be really, really good, right? That will be highly, highly productive water, and we will begin next time with doing that. And so basically, right, we've got we got a few things. We got sorry, bam. Let me just read this slide, right? Water depth, right? Pelagic zone, living in the water at any depth. Benthic zone, living in or on the bottom, and then the abyssal zone, living in or on the bottom, but in deep water. And now you're going to have to deal with that pressure. You have to deal with that sunlight. You have to deal with that cold water. But you have to deal with not a whole lot to eat, not a whole lot of food, but there are a lot of nutrients, which we will talk about next time in terms of bringing all those nutrients up from the bottom. And like I said, we'll talk about that next time. Okay, I'm going to reset some things, and then I'm going to talk about the lab. So I'll be, from your point of view, I'll be right back, and let me go do this. Okay, everyone, I'm back, and I've got the lab exercise, which I will have unlocked by the time you are watching this, up here in the little part of my monitor where I'm recording. And so normally we would have this lab, and I would have water around the room, and you would be measuring its density and its temperature and stuff. We can't do that, so I gave you some data. So first of all, we can see here in this first chart, for salinities of 2, 4, 6, and 8%, we have densities of 1.02, 1.035, 1.04, and 1.052, right? Not a huge range of density differences, but that's okay. So, in general, what's the relationship between salinity and density? I talked about that in the lecture. We can do a wee bit of math here to calculate the change in density per percent change in salinity. So if we go from 2 to 8%, if we subtract those two numbers, and then we go from 1.02002 to 1.052, we can subtract those two numbers. We can divide B by A, and that will tell us how much the density changes per degree change in salinity, right? So just follow that through, and that'll be fine. And so then I just put it in words. For every percent change in salinity, the density change is what? It's the same as this number. It's just in a sentence, that's all. And then think about a little bit, the range of seawater goes from 1 to 4% generally. So what's the density range of seawater, right? Now you're going to have to extrapolate a little because 1% isn't on the graph, but 2% is. And you just kind of figured out how much per percent. So you should be able to get to, what 1% is. And so just kind of think about that. And then, what about if the average density of seawater is 3.5%, which it is? What density would that be? Well, you've got 2 and you've got 4, so you can work that out. So yeah, and then a little bit about temperature and density. If I have water of a temperature of 10 degrees Celsius, 25 degrees Celsius, or 35 degrees Celsius, there's the density numbers. You don't need to worry about this because you're not actually measuring it. And then, the same kinds of questions, right? What's the general relationship between temperature and density? using the same math, what's the change in density per degree change in temperature? Subtract these, subtract 35 from 10, subtract 1.04, 1.031, divide those numbers like you did up here, and that will tell you the same thing, but now for degree of temperature Celsius rather than percent salinity. And then, which would have higher density, surface water at the pole or surface water at the equator? Think about that. Which would have higher density, shallow sunlit water, dark deep water, and we should know these just basically from the lecture. And then based on your data, which would seem to have the greater effect on density, temperature, or salinity? So think about that a little bit. And then there's a thing that we do where I have solutions of 3 different salinities. If you're really careful, you can get them to stack like that in a beaker. And so I say, okay, look, if I have, red, white, and green solutions, colored solutions stacked up like that, which is the most dense, which is the least dense, what color should be on top, what color should be on the bottom, given, their densities. That's kind of asking the same question twice. I should probably eliminate those, but whatever. And then, if these were different temperatures rather than densities, which layer would be the warmest, which layer would be the coolest, and which layer would be, intermediate in temperature, right? And so it's a very short lab, but it's, it's kind of interesting to think about these kinds of things. So anyway, do that, stick in the Dropbox. And by the way, that is the last lab of the semester. There will be no more labs. That's it. Okay, so once you're done with that, you're done with labs, right? And so now you can go back and fill in anything else that you have, and we'll be good to go. So anyway, like I said, by the time you're watching this, that'll be unlocked. So, okay, guys, continue to take care. Get me if you have any questions, okay? Okay, everyone, take care. Bye-bye.